how do we define the 6 trig functions for a point not on the unit circle? We picked a random point, x, y. We labeled the distance to the origin, r. We sort of visualized it as a triangle, right? So we we're thinking of this triangle, and we sort of applied the idea of SOHCAHTOA. In quadrant 1, both x and y are positive, so there's no mysteries here. And you just basically come up with these rules. Opposite over hypotenuse looks like this now. Adjacent over hypotenuse is x over r, and tangent is y over x. Now this is, of course, if x is not 0. If you have x equals 0, you have some problems there. Cosecant is r over y. Secant is r over x. Cotangent is x over y. Unless y is 0, then we don't have a secant. I mean a cotangent. Also, y cannot be 0 for the cosecant, and x cannot be 0 for the secant. In other words, the denominator can never be 0. Now you might say, what about sine and cosine? What if r was 0? Well, I already told you we're not going to be dealing with r equals 0 case. So we'll just write r is greater than 0. That means we're not allowed to talk about the origin. And normally they don't give you all 3 x, y, and r. You have to use the Pythagorean theorem to get your missing value. So in blue, I added these 2 rules. One is a condition. R is greater than 0. That's a requirement to use these rules. And the other one is just good old Pythagorean theorem as you know it. Notice there are strict rules for tan, cosecant, secant, and cotan. We cannot allow either x or y to be 0 in some of those cases. But we don't have that problem with sine and cosine because r is never 0 anyway. Question?
Is it okay to just consider R1 a constant or R is specifically?
Well, no, because let's look at our first example, and you'll see that they've designed it where r cannot possibly be 1. Okay, so let's go ahead and look at our first example. So you'll be doing a couple like these tonight. The question just says, let p, -1, -2 be a point on the terminal side of an angle theta. Plot. So how do you draw a diagram for this given? It's really not very hard. You're going to plot the point, -1, -2. A little hard if your pencil doesn't work. Okay. All right, so first thing we'll do is plot -1, -2. Okay, so get that going. I'll plot it in red. I'd like to draw the reference draw the angle and the reference angle, or theta ref, it's called, theta ref. So how do you do that? Well, it's talking about an angle that passes through this point, right? So your angle theta, don't miss this. You have to draw pictures on my test to show me that you understand the vocabulary, okay? You have to draw this and label it theta, okay? And then you have to draw the reference angle and label it theta ref. That's this little guy in green. The reference angle is the angle between the terminal ray and the nearest x-axis. In this case, that'd be the left side of the x-axis. Okay, so we did A and B. Okay, now it's time to find the 6 trig functions. And we'll be using our definition from the previous page. Okay, so let me go back and let's look at those definitions one more time. I'd like a quick way to memorize this. So, how about this? Sine is y over r, cosine is x over r, tangent is y over x, circ, slurc, tix. Let's all say that 3 times together. Ready? Begin. Circ, slurc, slur, tix. Again. Circ, slurc, slur, tix. Circ, slurc, slur, tix. Alright. I don't even know if I'm saying that right. But that's how it works. Okay, so we're using xertics. Weird. Okay, it's really just SOHCAHTOA. It's a little more useful though because we can use negative x's and negative y's and such. Okay, so we're going to write sine of theta is y over r. Right? Y over r. Y was actually given. Look back at the problem. It was the point -1, -2. So y was given all along. If the point is -1, -2, then we're just going to simply use -2 over r. So what is r? Well, this is the side you don't know. So we're going to run the Pythagorean theorem to get it. Remember, x squared plus y squared is always r squared. X is clearly -1, y is -2, r is unknown. We get 5 equals r squared, and we square root. We do not do the plus or minus because we have a rule about r being positive. Okay, so we do know r now. We put that in right here. Okay, I have a radical on the bottom, but I'll take care of that later. Let's go on to xer. I don't know how to say it. CXR. Xer. Anyway, it's x over r, and x is clearly -1. We've known that from the get-go. R we've just found, it's root 5. We'll clean up the denominator later. Okay, next is tan. Well, tan is something I could have done at the outset of the problem. It's just y over x. They gave me y and x. -2 over -1. So the answer is 2. Okay, let's go down and do our 3 reciprocal functions. So cosecant theta would be the reciprocal of sine. So that's -root 5 over 2. Secant theta, that's the reciprocal of cosine. So that's -root 5 over 1, or just -root 5. And cotangent theta is the reciprocal of 2, namely half. Notice these are not opposite reciprocals, they're just reciprocals, okay? So don't mess that up. Now let's go back, and if there are any denominators that have radicals, we'll clean that up. So this happens on just the sine and cosine here. I need to multiply by root 5, top and bottom. So my sine properly rationalized is -2 rad 5 over 5. Cosine, properly rationalized, is -root 5 over 5. And the rest of these were good to go. There was nothing wrong with them in the first place. There was no radicals on the bottom. Can someone tell me why I waited to the end to take care of the radicals on the bottom? Yeah, Ryan?
For cosecant, essentially. So when you did a reciprocal, the radical is
Yeah, if you take a fraction that has a radical on the top, right, and you flip it over to get, let's say, secant, you're going to have it on the bottom again. You're going to have to rationalize all over again. But if you do all your 6 fractions first, you'll find that there are fewer things to rationalize. So go back and clean up the radicals after. Just a little street smart thing, you know, thing I learned from doing it the hard way many times. Rationalize last. But don't forget to do it, right? It's still kind of important. All right, let's go to lesson 5.3. Sorry, that's kind of messy there. I was going to clear that page. Okay, let's talk about the properties of trig functions. So 5.3 is loaded with lots of little facts that you could learn on your own just goofing around on your calculator, okay? But it would take a while. So, for example, if you typed sine of 20 degrees, sine of 30 degrees, sine of 40 degrees, sine of 50 degrees, sine of 60 degrees, sine of 70 degrees, sine of 80 degrees, and sine of 90 degrees, you would find that those numbers are growing, interesting, and getting closer and closer to 1. So the values would be decimals, and they would grow all the way up to 1. Then you type, wonder what happens if I go sine 100. And if you type sine of 100, it goes back down. Interesting. So it goes up to 1 and then back down when you get to 90. Interesting. That's something you could easily investigate on your calculators. Put in degrees mode, go to sine 10, sine 20, sine 30, sine 40, sine 50, sine 90, sine 100. You can see the pattern building.
There were sine waves before?
Yes, that's where a sine wave comes from. So we notice certain things, like it seems like sine always gives us a decimal, except sometimes it gives us exactly 0 or 1, but it never gives us like 1.6 or 2.4. It never gives us 10. No matter what you type, sine whatever always comes out to less than 1 or greater than -1. So there's all these rules that you could get from playing around. Cosine's kind of like that too. But when you do cos 10, sine, cos 20, cos 30, cos 40, cos 50, cos 60, cos 70, cos 80, cos 90, the numbers are actually dropping from uno down to 0. So like you'll notice that on your calculator. Like when you get to like cos 90, you get exactly 0. It's not 1 anymore. So they're decreasing. Interesting. If you're doing tangent, that's a fun one. You could type tan 10, 20, 30, 40, 50, 60, 70, 10, 80, 10, 90 doesn't work, but you could try things like 10, 81, 10, 82, 10, 89, 10, 89.9, 10, 89.9999999, and you're getting answers like 500 million, and it's weird. You're getting all sorts of big numbers now. So you get the impression that like 10 can produce any number or something, and there's all these rules, and that's what we need to talk about. Okay? So usually when we talk about these sorts of things, we talk about what numbers we're allowed to type. Then we go back and ask, okay, what kinds of answers does the calculator give me? Those are the questions of domain and range, respectively. Okay, so let's talk about our first function. The name of the function is sine x. I probably shouldn't use x. The book does, but I'm going to use theta, because I don't want you to think that x is the same x we saw in our diagrams a minute ago. Okay, what is the domain of sine theta? This is like asking, if you pulled out your calculator and you type sine something, is there a something you cannot type? Is there some number you could do sine of it and then it would say error on the screen? Well, you might say no. Every time I press sine something, I always get an answer. You're right, it's all real numbers. But how do you prove that? Well, let's think about what it means. Sine, and let's go back to the unit circle definition just for simplicity. Sine basically means, on the unit circle, the y-coordinate of the point. So let me ask you a question. With all these green points going around the circle, are there any that don't have a y-coordinate? No, they all have a y-coordinate. Of course they do. So every possible point on the unit circle has a y-coordinate, therefore every possible angle in the world has a sine value. So there are no forbidden angles when you're typing sine of something. You type sine whatever you want. Sine pi, sine e, sine square root of 62. You always get an output. Okay? Let's go to cosine. Is cosine that way? Is cosine that forgiving? Yes. Cosine has domain all real numbers as well. The question is simply asking, for each green dot I showed here, do they all have x coordinates? And the answer is, of course, yes. Of course they all have x coordinates. They all have an x, they all have a y, they all have a cosine, they all have a sine. There's no exceptions. Okay, things get interesting when you start talking about tan, though, right? Tangent, sometimes when you type tan something on your calculator, it's kind of rare, but you might type tan something and then it says error. What's going on there? Well, tangent is defined as y over x, right? So now let's look at the circle again. Can you think of any points on here where the coordinates will not allow me to divide y over x? 90. And yes, this does happen in 90, doesn't it? Right at the top of the circle, we have a culprit, 0, 1. We have problems with y over x here, see? Where is this, the top of the circle? What angle is that? 90. Okay, so we see that 90 is forbidden. Unlike sine and cosine, we do have an issue with 90. 90 degrees has an x-coordinate, has a y-coordinate, but it doesn't have a y over x. See? That's what's going on there. Are there any other spots in the circle where we have this problem? 270. Yes, you're right. 270 has the same problem. Negative 1 over 0 doesn't exist. So 270 is forbidden from the domain as well, see? Now I could just tell you the facts, or we can think them through like this, right? It's probably better for us if we just think it through. So you can try typing tan 270 on your calculator, and if it's in degree mode, it will say error, okay? Are there any other angles that are forbidden? How about, you're going to say, oh, I didn't know you meant that. How about negative 90? Is that allowed? What does that mean, negative 90?
Going clockwise.
Okay, that means clockwise 90. Doesn't that put us in the same problem as 270? That puts us in the same spot, right? So because negative 90 is coterminal with 270, we have issues with that as well. What if you went this direction? So we're talking about negatives now. What if you went around 3/4 of a circle? In other words, negative 270. That would be a problem too, right? You would end up at the top of the circle again, and that's forbidden. We're going to write down a formula for this in just a second. I'm trying to get you to see the pattern. Isn't it true also that if I talk about the angle 450, I have problems? What does 450 mean? It's a full circle, 360, plus another 90. So I'll do that in purple here. If you go a full 360 degrees in the positive direction, you end up right here where my arrowhead is. But if you keep going another 90, you're at the angle 450. But that's coterminal with 90. That's the same spot. So we have issues with 450 as well. So there is a pattern building here. 90 is 1 times 90, and 270 is 3 times 90, and 450 is 5 times 90. So 1 times 90 is forbidden, 3 times 90 is forbidden, 5 times 90 is forbidden, negative 1 times 90 is forbidden, negative 3 times 90 is forbidden. Can you tell me what kinds of numbers are forbidden? Odd multiples of 90 are forbidden. So odd multiples of 90 is a nicer way to say this, and that's how we'll write it. So when he writes this, I'm going to put x cannot be an odd multiple of 90, or as we write mathematically, theta cannot be 2k plus 1 times pi over 2. You might say, what is that? Listen, 2k plus 1 is math code for odd number.